Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A towering problem, one of the great beasts of 9th century mathematics, still roamed the halls of algebra in the 1940s. The classification of complex, semisimple Lie algebras, those fundamental symmetries underpinning geometry and physics, have been tamed, in a sense, by the heroic efforts of Wilhelm Killing and a monumental genius of the Lie Cartan. Their work was a landmark, a vast and intricate cathedral of thought, yet its foundations contained unsettling gaps in logic, and its architecture was so labyrinthine that few could navigate it with confidence. The proofs were notoriously opaque, relying on case-by-case analyses that felt more like acts of sheer computational than elegant demonstrations of a deeper truth. The problem lingered, a masterpiece with a flawed pedigree, awaiting a mind that could see its essential structure with absolute clarity. That mind belonged to a young student at Moscow State University, Yevgeny Dynkin. At the age of 20, while still an undergraduate, he entered the legendary seminar of Israel Gelfand. The Gelfand seminar was the crucible of Soviet mathematics, a place where the air crackled with intellectual energy and where the grand challenges of functional analysis and representation theory were confronted head-on. It was within this demanding environment that Dynkin, under Gelfand's supervision, turned his attention to Cartan's magnificent yet perplexing classification. He embarked on a project that would produce one of the most elegant and powerful tools in modern mathematics. Dynkin's approach was an act of profound conceptual translation. He recognized that the intricate algebraic relationships governing the structure of these algebras, the commutation relations, the eigenspaces, could be entirely recast in a simpler, visual language. He distilled the essence of the problem into a combinatorial object, a simple graph that would come to bear his name, the Dynkin diagram. This invention transformed the landscape. The abstract, high-dimensional geometry of route systems, which described how the algebra acts on itself, became a tangible network of nodes and lines. The methodology is a model of mathematical elegance. In the Dynkin diagram, each node represents a simple route, one of the fundamental building blocks of the algebra's route system. The way these nodes are connected reveals everything essential about their relationship. A single line between two nodes indicates that the corresponding routes sit at an angle of 120 degrees to each other. A double line signifies an angle of 135 degrees, and a triple line, 150 degrees. If two nodes are unconnected, their routes are orthogonal at a 90-degree angle. For connections involving routes of different lengths, a small arrow is placed on the edge, pointing from the longer route to the shorter one. This simple set of rules encodes all the necessary information. Impossibly complex algebraic structure, defined by hundreds of equations, was now represented by a small, clean drawing. The problem of classifying all possible complex semisimple Lie algebras was thereby converted into a much more tractable one. Find all possible graphs that can be constructed according to these rules. This is a problem in elementary geometry and combinatorics, and Dynkin solved it completely. His 1947 paper, The Structure of Semisimple Lie Algebras, published in the journal Aspekte mathematических наук, laid out the stunning result. The seemingly infinite variety of these algebraic structures collapsed into a remarkably finite and orderly classification. There are 4 infinite families, which he labeled a sub n, b sub n, c sub n, and d sub n, corresponding to the classical Lie algebras associated with special linear, orthogonal, and symplectic groups. And then there are 5 exceptional, solitary structures, objects of unique and beautiful symmetry that fit nowhere else. These are the famous exceptional Lie algebras G2, F4, E6, E7, and E8. The beast had been fully mapped, its entire anatomy revealed. Dynkin's work provided a rigorous, complete, and breathtakingly simple proof of the classification that had eluded his predecessors. He also introduced powerful supplementary concepts, like the maximal route, to streamline the analysis and reveal further layers of structure within the algebras. The intellectual lineage of this achievement is clear. It was a direct and brilliant clarification of the path forged by Lie Cartan. Dynkin took Cartan's conclusions, which were correct, and placed them on an unshakable logical foundation, making the deep truth of the classification accessible to a new generation. The environment created by Israel Gelfand was a catalyst. Gelfand's focus on representation theory, the study of how abstract groups manifest as concrete transformations, highlighted the immense importance of having a clear, usable map of the fundamental Lie algebras. The impact of Dynkin's diagrammatic method was immediate and transformative. It became the standard language for the field. The American mathematician Bertram Constant, a leading figure in representation theory, would later build vast portions of his own work on the geometric insights provided by Dynkin diagrams, using them to unlock deep properties of Lie group representations. When the influential French mathematician Jean-Pierre Serre wrote his now canonical textbook, Complex Semisimple Lie Algebras, he structured the entire exposition around Dynkin's approach. This act cemented the diagrams as a central pedagogical and research tool for all that followed. Today, the utility of these diagrams extends far beyond pure mathematics. They appear in the most advanced theories of theoretical physics. In the quest for grand unified theory, or GUT, physicists use Dynkin diagrams to classify the possible gauge groups that could unify the electromagnetic, weak, and strong nuclear forces. The diagrams for E6, E7, and E8, once seen as beautiful mathematical curiosities, are now central to explorations in string theory and M-theory, where they describe fundamental symmetries of the universe at its most microscopic level. What began as a young student's effort to clean up a century-old problem has become an indispensable part of the modern physicist's toolkit, a testament to the profound and often unexpected unity of abstract mathematical structure and the physical world. For any graduate student beginning a journey into mathematics or theoretical physics, learning to read and work with Dynkin diagrams is a rite of passage, a first encounter with a tool of almost magical power and simplicity. This early triumph revealed a mind drawn to the discovery of fundamental, unifying structures, a theme that would continue to resonate throughout his career, even as he turned his gaze toward an entirely different mathematical domain. The search for fundamental, unifying structures that animated his algebraic work found a new, dynamic renewing probability theory. This intellectual pivot, occurring in the late 1940s and early 1950s, represented a profound shift in subject matter, yet a remarkable continuity in spirit. The intellectual ferment of Moscow State University, particularly the legendary seminar he co-led with his mentor Israel Gelfand, provided the perfect crucible for such a transformation. These seminars were famous for their demanding atmosphere and their disregard for disciplinary boundaries. Here, ideas from functional analysis, group theory, and differential equations were thrown together, creating a vibrant intellectual ecosystem where a mind like Dynkin's could see connections others missed. He began to perceive that the random, seemingly unpredictable paths of stochastic processes might themselves be governed by a deeper, underlying analytic structure, one that could be captured with the same rigor he had applied to the classification of Lie algebras. At the time, probability theory was undergoing its own maturation. Andrew Kolmogorov, 2 decades prior, placed the field on a firm axiomatic foundation with his measure-theoretic framework, defining probability as a particular kind of measure on a space of outcomes. This was the bedrock building upon it. Mathematicians like William Feller were exploring the behavior of specific classes of random processes over time, particularly through the lens of one-parameter semigroups and their associated infinitesimal generators. These generators were differential operators that described the instantaneous rate of change of the process. The theory was powerful, yet it was largely tailored to processes with certain convenient properties, a grand, unifying theory that could handle a much broader class of processes, particularly the rich family of strong Markov processes, and connect them systematically to the vast machinery of modern analysis, was still waiting to be built. This was a challenge Dynkin embraced. He sought a universal language to describe the evolution of a Markov process, a tool that would fully encapsulate its probabilistic soul within an analytic body. His solution was the introduction of the characteristic operator. This concept was a powerful generalization of Feller's infinitesimal generator for any strong Markov process, which includes a vast array of random walks, diffusions like Brownian motion, and jump processes. Dynkin defined an operator, let us call it A, that acts on a suitable class of functions. This operator captures the expected instantaneous behavior of the process. If you take a smooth function f and apply the operator to it, the result, f evaluated at a point x, tells you the expected rate of change of the function f along the random path starting from x. The operator became a complete analytic signature of the process. The genius of this approach lay in the bridge it constructed between two worlds. The study of the random, path-dependent evolution of a system was now inextricably linked to the study of the deterministic, analytic operator. Questions about the long-term behavior of a process, the probability of it hitting a certain set, or its average value over time could be translated into questions about the domain of the operator A, its spectral properties, or the solutions to equations involving it. Specifically, this forged a profound connection to the theory of elliptic and parabolic partial differential equations. The characteristic operator for Brownian motion, for instance, is proportional to the Laplacian operator, the very heart of the Laplace equation, and the heat equation. Suddenly, centuries of knowledge about potential theory and diffusion equations could be brought to bear on problems in probability. A random walk could be understood by studying the discrete version of the Laplacian. The probabilistic behavior of a particle diffusing through a medium was mirrored in the analytic solutions of the heat equation. The supreme articulation of this powerful connection is a result known as Dynkin's formula. It stands as a cornerstone of the modern theory of stochastic processes, an elegant and immensely practical tool. In its spoken form, the formula states that the expected value of the function f, evaluated at the position of a stopped process x at a random time tau, starting from a point x, is equal to the value of the function at the starting point, f of x, plus the expected value of the integral from time 0 to tau of the characteristic operator applied to f, evaluated along the process path x sub s. Symbolically, we would write the expectation, starting from x, of f of x sub tau equals f of x, plus the expectation, starting from x, of the integral from 0 to tau over f of x sub sts. This formula is a thing of beauty. It provides an explicit recipe for computing a probabilistic quantity and expected value by performing an analytic calculation involving the characteristic operator. It is a generalization of the famous Ito's formula from stochastic calculus and serves as a fundamental computational and theoretical device. This entire framework was systematically laid out in his 1959 monograph, Foundations of the Theory of Markov Processes, a book that redefined the field for generation. His work, while revolutionary, stood on the shoulders of giants. He built directly upon the mesh-theoretic world created by Kolmogorov. He generalized and abstracted the seminal ideas on generators pioneered by Feller, and his development ran in parallel with the burgeoning theory of stochastic calculus being forged by Kiyoshi Ito in Japan, with both approaches providing complementary ways to understand the intricate behavior of diffusion processes. Dynkin's unique contribution was the creation of a comprehensive, operator-theoretic viewpoint that unified these threads into a coherent and powerful whole. The impact was immediate and transformative. A new school of probability theory emerged, one centered on the deep interplay with analysis. In the United States, his work directly shaped the research of future luminaries. Srinivasa Barahan, a recipient of the Abel Prize, took Dynkin's operator-centric view and used it to develop the martingale problem formulation for Markov processes, which has become one of the most powerful and flexible ways to define and analyze stochastic processes. Frank Knight, another leading American probabilist, built upon Dynkin's foundations in his own profound work on prediction processes and the structure of Markovian systems. The modern theory of stochastic analysis, a staple of graduate programs in mathematics, statistics, and even quantitative finance, is unthinkable without the bridge that Dynkin built. The idea that Brownian motion and the heat equation are two sides of the same coin is now a fundamental pedagogical concept, providing the theoretical underpinning for everything from modeling stock prices to understanding heat flow. Through this monumental effort, Dynkin revealed that beneath the chaotic dance of randomness lies the elegant, predictable structure of analysis. Within this grand architecture, he also crafted smaller, exquisitely precise tools, instruments designed for the foundational work of proof itself. Within this grand architecture of connecting random processes to analysis, Yevgeny Dynkin also crafted crafted smaller, exquisitely precise tools, instruments designed for the foundational work of proof itself. Mathematics, particularly in its purest forms, often advances through the creation of such conceptual machinery, an entire field to be held back by a recurring technical difficulty, a chasm that must be crossed again and again in countless proofs. For the generation of mathematicians building upon the measure-theoretic foundations laid by Emile Borel and Henry Lebesgue, one such chasm was the problem of extension. The challenge was ubiquitous and profound, but one could often establish a desirable property for a simple, well-behaved collection of sets, say, all the intervals on the real line, but the goal was to show that this same property held for every set in the vast, complex universe generated by those simple ones, the so-called Borel-Sigma algebra. Proving this leap from the simple to the complex frequently involved clunky, bespoke arguments, often relying on a cumbersome technique known as the monotone class theorem. It was a process that worked, yet it lacked elegance and felt more like heavy engineering than insightful mathematics. Dynkin's response to this recurring inconvenience was a piece of intellectual artistry of the highest order. He forged a tool so perfectly suited to this task that it has become a cornerstone of modern probability theory, a device celebrated for its power and its almost magical simplicity. This contribution is the pi-lambda theorem, sometimes called the Dynkin system theorem. To appreciate its genius, one must first understand the components of this elegant machine. He introduced a structure, now commonly called a Dynkin system, though he originally named it a lambda system. This is a collection of subsets of a given space that satisfies three modest conditions. First, it must contain the whole space. Second, if a set is in the system, then its complement must also be in the system. Third, the system must be closed under countable unions of disjoint sets. These conditions are similar to, yet weaker than, the defining properties of a full sigma algebra, which requires closure under countable unions of any sets, disjoint or otherwise. This slight relaxation of the rules is the key to the entire construction. The second component is what he called a pi system, a term that has become standard. A pi system is a collection of sets with an even simpler property. It is closed under finite intersections. If you take any two sets from a pi system, their intersection must also be in the system. Many natural collections of sets are pi systems. For instance, the collection of all intervals on the real line is a pi system because the intersection of any two intervals is another interval or the empty set. Having defined these two structures, Dynkin delivered the theorem that connects them. The pi-lambda theorem states that if a pi system is contained within a lambda system, then the entire sigma algebra generated by that pi system must also be contained within the lambda system. The practical consequence of this statement is breathtaking. It provides a clean, three-step recipe for solving the very extension problem that had vexed mathematicians. Instead of wrestling with the monstrous complexity of a sigma algebra, a mathematician could now follow a simple program. First, identify a simple pi system that generates the sigma algebra of interest. Second, show that the desired property holds for every set in that simple pi system. Third, demonstrate that the collection of all sets having the property forms a lambda system. Once these three steps are complete, the pi-lambda theorem acts like a logical switch, instantly guaranteeing the property extends to all sets in the full sigma algebra. The difficult leap across the chasm becomes a sequence of three manageable steps on solid ground. A classic and beautiful application illustrates the theorem's power, proving the uniqueness of probability measures. Suppose we have two probability measures, which we can call P and Q, defined on the same measurable space. We want to know if they are the same measure. That is, does P ever equal Q for every single event in our sigma algebra? Let us assume we can verify that they agree on a simple class of sets. For example, all intervals of the form open parenthesis negative infinity comma x close bracket on the real line. This collection of intervals forms a pi system. Now we define a new collection of sets. Let's call it D, consisting of all the events for which P of a does equal Q of a. Our goal is to show that D contains every set in the Borel sigma algebra. Using Dynkin's machine, the proof is swift. We first verify that our collection D is a lambda system. This verification is a direct, almost mechanical exercise using the basic axioms of probability. For instance, if A is in D, meaning P of R equals Q of R, then P of a complement, which is 1 minus P of R, must equal Q of a complement, which is 1 minus Q of R. So A complement is also in D. Similar checks confirm the other lambda system properties. We already established that our simple collection of intervals is a pi system by our initial assumption P and Q agree on these intervals. So this pi system is contained within our lambda system D. At this point, the pi-lambda theorem does all the remaining work. It concludes that the entire sigma algebra generated by the intervals the full Borel sigma algebra must be contained within D. Therefore, P over equals Q over for every Borel set. The two measures are identical. The proof is complete. Its elegance a testament to the quality of the tool employed. This theorem was a direct product of the intellectual environment Dynkin inhabited. Its necessity arose from the very problems he was tackling in the theory of Markov processes, where such extension arguments are a constant feature of the landscape. It was a tool he built because he needed it for his larger project. Yet its influence spread far beyond his own work, becoming a fundamental part of the toolkit for anyone working in measure-theoretic probability. In his celebrated textbook, Probability with Martingales, the British mathematician David Williams introduces the pi-lambda theorem with an almost reverential tone, calling it a result that you may find yourself using over and over again. Another leading probabilist, Rick Durrett, makes it a cornerstone of the introductory chapters of his widely used text, Probability Theory and Examples. Through its adoption by educators like Williams and Durrett, Dynkin's theorem has shaped the way generations of graduate students in mathematics, statistics, mathematical finance learn to think and to construct proofs. It is a piece of pure, abstract mathematics that functions as an indispensable device for the working theorist. The creation of the pi-lambda theorem reveals a particular quality of Dynkin's mathematical mind, a capacity for seeing the essential structure of a recurring difficulty and abstracting it into a clean, powerful, and reusable solution. He possessed an immense talent for classification, for finding the right definitions that would make the hidden architecture of a subject visible. This same intellectual drive, this pursuit of the fundamental structures underlying complex phenomena, animated his entire career. The same energy that allowed him to classify semisimple Lie algebras and to build a foundational tool for measure theory would soon be directed toward new horizons, propelled by historical forces that would irrevocably alter the course of his life and his research. The pi-lambda theorem, a testament to Dynkin's capacity for elegant abstraction, stands as a pivotal achievement. Its creation reveals a remarkable ability to discern the fundamental structure of recurring mathematical challenges, transforming them into refined, powerful, and reusable solutions. This inherent talent for classification, for illuminating the hidden architecture of a subject through precise definitions, characterized his entire mathematical journey. This relentless pursuit of underlying structures, a hallmark of his work with semisimple Lie algebras, would soon find a new focus, propelled by external forces that reshaped both his life and his research trajectory. His emigration to the United States in 1976 marked a profound turning point. The political pressures he faced in the Soviet Union, while undoubtedly difficult, inadvertently cleared the path for a remarkable professional renaissance at Cornell University. This new chapter witnessed the emergence of a different kind of mathematical architecture, one built not on the rigid symmetries of Lie algebras, but on the stochastic fluctuations of branching populations. The challenge he tackled here was formidable, modeling the collective behavior of vast, spatially distributed populations of individuals undergoing random movement and reproduction, a problem that defied classical individual-based approaches. Such models, while conceptually straightforward, become computationally intractable when dealing with a large number of interacting entities. The need for more efficient, macroscopic description became apparent. Dynkin's response was the creation of the theory of superprocesses, a significant contribution to the field of stochastic processes. This elegant mathematical framework sidesteps the complexities of tracking individual particles. Instead, it focuses on the evolution of a random measure representing the population's mass distribution across space. This shift in perspective, from discrete individuals to a continuous density, provided a powerful new tool for analyzing population dynamics. The very essence of this innovation lay in its capacity to capture the collective behavior of a multitude of entities as a unified mathematical object. Central to Dynkin's contribution is his isomorphism theorem, a landmark result that established a profound connection between superprocesses and the solutions of specific nonlinear partial differential equations, PDES. This theorem served as a bridge, connecting the probabilistic world of random measures to the deterministic realm of analysis, revealing a hidden symmetry between two seemingly disparate mathematical domains. This was no mere analogy. It was a precise mathematical equivalence, offering a powerful new method for calculating probabilities and expectations related to superprocesses. The solution to these probabilistic problems could be found through the solution of a corresponding PDE. The archetypal example of a superprocess is super-Brownian motion. This process describes a cloud of branching particles, where individual particles move according to Brownian motion, a fundamental model of random walk. The corresponding analytical counterpart, reflecting the population densities, evolution, is described by a specific nonlinear heat equation of the partial derivative of u with respect to t equals 1/2 times the Laplacian of u minus u squared. Dynkin's isomorphism provides a precise, calculable link between the probabilistic behavior of the super-Brownian motion and the solution of this PDE. This profound connection is not simply a mathematical curiosity. It offers a practical pathway for analyzing complex population dynamics. The impact of Dynkin's work reverberates throughout the field of probability theory. His monograph, An Introduction to Branching Measure Value Processes, stands as the definitive text on his approach, codifying the techniques and theoretical underpinnings of superprocess theory. This work didn't emerge in isolation. He engaged in a rich intellectual exchange with other leading probabilists, most notably Donald A. Dorson and Cameter, who independently developed related ideas. The work of Harry Keston on branching random walks also provided essential context and inspiration. These researchers, though pursuing independent lines of inquiry, found themselves exploring related mathematical landscapes, their work informing and enriching one another. Dynkin's contribution, however, extended far beyond its immediate impact on his contemporaries. His work essentially launched a new subfield of probability theory. It directly influenced the research of Jean-François Gall, who employed the innovative Brownian snake construction to delve deeper into the intricate geometric structure of super-Brownian motion. Similarly, Ed Perkins built upon Dynkin's foundation, focusing his research extensively on the measure-theoretic properties and the intricate sample path behavior of these processes. These researchers, and many others, stand as direct beneficiaries of Dynkin's intellectual legacy. Their work, in turn, continues to expand and refine a theoretical framework he initially established. This chapter in Dynkin's career, marked by his emigration and his subsequent work on superprocesses, demonstrates a remarkable adaptability and a sustained commitment to uncovering fundamental mathematical structures. The same intellectual drive that led him to classify semisimple Lie algebras and to create the pi-lambda theorem is clearly visible in his exploration of branching processes. His work is a testament to the enduring power of mathematical abstraction, capable of bridging seemingly disparate fields and revealing hidden connections between seemingly unrelated mathematical worlds. This ability to synthesize diverse mathematical domains would continue to shape his enduring legacy. To survey the arc of Yevgeny Dynkin's career is to witness a profound intellectual journey, one that traversed continents, political systems, and even the internal territories of mathematics itself. His passage from the algebraic certainties of Lie groups to the fluctuating realities of stochastic processes might appear as a dramatic rupture, a tale of two distinct scientific lives. Yet, a deeper examination reveals a powerful, unifying current flowing beneath these surface shifts. The core of Dynkin's genius lay in a singular, relentless pursuit of the identification and classification of fundamental structures. His entire oeuvre represents a masterclass in finding the precise language, the correct representation that allows a complex system's essential architecture to become luminously clear. The same intellectual temperament that gave us the elegant combinatorial clarity of Dynkin diagrams was at play in his later work on probability. Consider the parallel. In the 1940s, working under the formidable influence of Israel Gelfand, Dynkin sought to bring order to the sprawling universe of semisimple Lie algebras. The problem was one of classification, of finding a finite, complete, and non-redundant list of these foundational algebraic objects. His solution, the Dynkin diagram, was a stroke of combinatorial genius. It translated the abstract, high-dimensional properties of an algebra into a simple, visual graph of nodes and lines. The profound properties of the algebraic structure, its representations, could be read directly from this diagrammatic skeleton. It found the system's DNA. Decades later, on another continent, facing the seemingly unbounded world of Markov processes, he confronted a conceptually analogous challenge. How does one classify the infinite variety of ways a system can evolve randomly in time? The solution, once again, was to find the object's infinitesimal generator, what he termed the characteristic operator. This operator, a differential or integral differential object, encodes the process's local behavior, its instantaneous tendencies to jump or drift. From this infinitesimal description, the entire global behavior of the process could be reconstructed. The characteristic operator for Markov process functions as the Dynkin diagram. Thus, for Lie algebra, it is the compact, essential key that unlocks the structure of the whole. The tools were different, one algebraic and combinatorial, the other analytic and probabilistic, but the philosophical quest was identical. It was a lifelong search for the mathematical seeds from which entire forests grow. This search for elemental structure inherently made Dynkin a builder of bridges. He operated in an era when the subdisciplines of mathematics were growing increasingly specialized, their practitioners speaking mutually unintelligible languages. Dynkin's work provided a Rosetta Stone. He demonstrated with irrefutable elegance that the theory of Lie groups, the analytic world of potential theory, and partial differential equations, and the dynamic realm of stochastic processes were deeply interconnected. His papers from the mid-1950s explicitly forged this connection, showing that questions about the long-term behavior of a Markov process could be translated into questions about the solutions to elliptic and parabolic equations, whose symmetries were in turn governed by Lie groups. He revealed these fields as different dialects for describing the same underlying reality of structure and transformation. This synthetic vision, which saw the unity between algebra and analysis, is perhaps his most enduring intellectual legacy. He taught mathematics to speak to itself. The tangible immortality of his contributions is now woven into the fabric of modern science and mathematics. In theoretical physics, from string theory to quantum field theory, the classification of fundamental particles and forces relies explicitly on the symmetries of Lie groups, and physicists sketch Dynkin diagrams as routinely as they write equations. They are an indispensable tool for understanding the fundamental symmetries of the universe. In every graduate level probability course, students encounter the pi-lambda theorem, a seemingly modest lemma that provides the essential scaffolding for building the entire edifice of modern measure theory. It is a testament to his pedagogical insight, a tool designed with the specific purpose of making a difficult, foundational concept accessible and rigorous. His work on superprocesses continues to fuel vibrant research at the frontiers of mathematical biology, population genetics, and mathematical finance, providing sophisticated models for systems characterized by branching, extinction, and complex interactions. Ultimately, the story of Yevgeny Dynkin is a testament to intellectual courage and the universality of mathematical truth. He reached the absolute summit of his profession twice. First, as a young prodigy in the unparalleled Moscow School of Mathematics, he became a world leader in algebra. Then, forced to begin anew in middle age, he relocated to Cornell University and, with astonishing speed, established himself as a dominant figure in modern probability theory. This was a reinvention born of necessity, but also of a profound internal consistency. The problems changed, the colleagues changed, the very continent changed, but the fundamental intellectual drive remained unaltered. His life demonstrates that the deepest structures of mathematical thought are recognizable to a prepared mind, irrespective of geography, specialty, or circumstance. He saw the same elegant skeletons of logic and form, whether they were clothed in the language of algebra in Moscow or the language of probability in Ithaca, reminding us that the world of pure reason is, in the end, a single, unified country.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.